This video is going to give you some idea about what the normal distribution is. And first, I want you to start looking at these two images. The title that we have down here is How Many Hours Do You Spend on Your Phone? And so each of these purple dots represents a person, and it tells us how much time they spend on their phone every day. So like this person, which is at 1, here's 2, here's 0, so this is 1, spends 1 hour on their phone. This person spends 2, these 1, 2, 3, 4, 5, 6 people spend 3 hours on their phone. And notice kind of what happens here is that you get a bunch of people kind of around the average, which apparently is 5 hours on the phone. Teenagers are wild. And then you have very few people who spend as much as 8 or 9 hours on their phone, very few people who spend very little time on their phone. And this creates what we call a normal distribution, where you have kind of a lot in the center and then few on the left and few on the right. So this right here is a dot plot. Well, this over here is what we call the normal curve. And the normal curve is calculated using all of the data from this dot plot. And the way that the normal curve is made is what we have is we have a mean, which is normally used with this symbol mu, and the mean in this case is 5. The mean happens to be right down the center itself. And then we also have what is called the standard deviation, which I'm going to talk about a little bit more in a minute, but the symbol that we use for that is a lowercase sigma, which looks kind of like an O with a hat or something. And what do we use this for? So we use it to look at populations of data, and this is a good example of how many hours do you spend on your phone. So the population is all of the people that we asked. But note, the data is only one variable. There's only one number per data point. So this is not a scatter plot. Lots of people tend to think of this as a scatter plot, but a scatter plot would be if you had like time and like, I don't know, beads made, something. And each of these data points would be two different numbers, right? It would be the number here, that's your x value, and then the number here would be your y value. That gives you two different numbers. So maybe it's like 4 and 3. So then this would be the 0.43. That's not what's happening down here. Each of these is just one number. This is a 5, this is a 5, this is a 5. It's just that we have a bunch of 5s here. Most numbers are around the average, so you'll see a lot more in the center. The data is approximately symmetric, so you'll notice that this side is pretty similar. It's not identical, but pretty similar to this side. And here, the normal curve, you will notice, is definitely symmetric. This side is the same as this side. And then you have very few really small and really large data points. So that is kind of what a normal curve looks like. So let's look a little bit more at the structure of the curve. As I said before, it is based on the mean, which is the average, and that isn't exactly in the center, of the data. And we normally use this symbol, which is just like a fancy M. It's called mu. It's a Greek letter, I think. Probably Greek. And that is just right here in the center. That is the mean. And then it is based on the standard deviation, which again is this symbol sigma. And that just describes how spread out the data is. And every normal curve, doesn't matter which one you're looking at, will have exactly this structure. Where you'll notice I've got all of these like -1 sigma, -2 sigma, -3 sigma. And what this is saying is, so if you have the mean, it's say -1 sigma and +1 sigma, so all of this area right here, that is plus or minus 1 standard deviation. And you'll notice this number here, 68% of our data lives in that area. Okay. That's not what I wanted to do. I want to get rid of that. Okay. 2 standard deviations, which is this blue section right here. In all of this, which includes obviously that first standard deviations. If you are within 2 standard deviations, that is 95% of all of the data. So 95% of everything will live in this area. And then finally, if you go all the way out to 3 standard deviations, which is everything all the way out to this pink line, and I did kind of a bad job over here, but you will get 99% of the data. So is it possible for you to have a data point if this thing extended all the way over here? Of course it is. Like, you could have a data point over here, but maybe it's a really, really, really rare one, right? This is the height of all of the high schoolers in the world. This is the height of Yao Ming, who is like 7'6", Chinese basketball player. Okay. And normal curves, here I have 3 of them. I have this red one, I have this purple one, and I have this blue one. Notice they have the same structure, right? They all have a mean right here in the center, and they all have those same 3, like, so here's 1 standard deviation, here's 2, and then all the way over here you'd get a third one. Here's 1, here's 2, and then you can see a tiny little third one right here. Here's 1, here's 2, and then over here there's, you can see that tiny little blue dot, that would be your third one. The third standard deviation is pretty small, but it depends on how big the mean is. That is where this thing sits on the x-axis. So the mean here is 0. The mean here would be at 1, 2, 3, 4, 5, so that's a 3. The mean here is at 8. And then the standard deviation for each of them is also different. In this case, the distance between the mean and each of the standard deviations is 1 unit. Over here it is half a unit, and then over here it is 2 units. And so the width of the standard deviation, like the smaller the standard deviation, the taller you're going to get this shape to be, because that means that it has to get all of that area in a sort of shorter period of time, whereas like this blue one, it's big and wide, so it kind of comes down a lot and it becomes a lot shorter because it has a lot more space to spread out here, and then obviously kind of a medium one. So the smaller the standard deviation, the taller and spikier it will be. The bigger the standard deviation, the longer and wider it will end up being. So last thing in this video, let's look at an example. So going back to the how much time do you spend on your phone every day? We have the curve, we have that the mean is 5 hours, which has put us right in the center. And the standard deviation in this case is 1.5 hours. So what I'm gonna do right now is I'm gonna mark out, I'm gonna say, okay, 5 plus 1.5 would get us to 6.5 hours. And 5 minus 1.5 would get us to 3.5 hours. So this right here is minus 1 standard deviation and plus 1 standard deviation from the mean. And if you remember that number there, what we're saying is that in this section right here, we have 68% of all of the data. So 68% of people use their phone for between 3.5 and 6.5 hours a day. And in this case, we are talking about teenagers. Okay, if we keep going here and we say, okay, go down another minus 1.5 and go up another plus 1.5, this now is minus 2 standard deviations or plus 2 standard deviations. Again, all of this from the mean. And then all of this area that is covered in pink now, this is about 95% of all of the data. And I'm just going to give myself a little bit more space if I can. Get rid of this because we don't need it. Sorry. Finally, if you go all the way out to, so another minus 1.5, and over here plus 1.5. So all of this space right here now covered by all of these, this is minus 3 standard deviations or plus 3 standard deviations, again from the mean, and this is now 99% of our data. So this says that 99% of people use their phone from between half an hour a day all the way up to 9.5 hours a day, which is the majority of everybody. Let me know what questions you've got.